All right, guys, we want to do a torque test on our servo gearbox that we constructed here. But first I want to talk a little bit more about torque. We should probably define it here. Torque equals force times distance. Okay, and when we're talking about force, it's important to recognize that force is actually a vector. It's not just 50 pounds, it's 50 pounds acting in some direction. A vector is a quantity that has both magnitude and direction. And so if we can think of our force as having a direction, then we can figure out what is the distance to that vector. And for those of you who have looked at my geometry lessons, you know that finding the distance to a line, if we're talking about the distance to a line, we're talking about finding the perpendicular distance. And let me just demonstrate really quickly what I mean by that. If we're talking about a force that has a certain amount of weight, let's go ahead and draw. We're going to hold a 10-pound weight in our hand, and we're just going to have this 10-pound weight right here. Okay, we're going to be standing here and we're holding this 10-pound weight. And if we try to bring this weight out here, if we swing our arm out here and we try to hold that 10-pound weight out here, well, here the direction of force is straight down. Remember, force equals mass times acceleration. And what is the acceleration that's acting on this mass? It's the acceleration due to gravity. So that means that this force becomes a vector acting in that direction. And likewise, even when we swing it out here, that vector doesn't change. It's still going down. So actually, when I'm holding this weight right here, if I want to figure out what the torque is on my shoulder, right here, it's 0. Because the distance to the line of force is 0. But let's say my arm is 3 feet long. When I try to swing that weight out here, I'm looking at, if that is straight down, then I'm looking for this perpendicular distance here in order to calculate the torque. And the torque here is going to be my 10 pounds times 3 feet, and that's going to give me 30 pound-feet of torque. Let's take a quick look again at some of our units of torque here. We just figured that out in foot-pounds, but these are all different units of torque that you're going to run into. Now, if you're looking at this with a critical eye, you might say, hold on, something here isn't right. A pound is a unit of force, and a foot is a unit of distance. So I can see that feet times distance times force. That makes sense. And I can convert that distance into inches, and I still have distance times force. And if I want to define an ounce as a 16th of a pound, then I'm still good there. And down here, a Newton meter is a unit of torque, because a Newton is a unit of force, but a kilogram and a gram are not actually units of force, they're units of mass. Technically, this is correct. And this is something you would definitely want to take into account if you were designing a robot that was not going to operate on Earth, but was going to operate on Mars. You'd want to take that into account, because remember I said force equals mass times acceleration. And the acceleration that we're talking about here in terms of the weight of an object is the acceleration due to gravity. So theoretically, I've got to multiply my mass times g, 9.81 meters per second squared, in order to get an actual unit of force, a Newton. But to be practical, since we are designing this robot on Earth and going to use it on Earth, we should probably just go ahead and work with these units here, because otherwise what we're doing is we're multiplying in the g every time, and then end up dividing it back out every time we want to find an amount of mass that a particular motor might be able to lift at a given distance. So for all practical purposes, we are going to use grams and kilograms sort of as if they were units of force, even though they're not. And this is going to be handy for us because, you know, all of the parts that we're working with goBilda these are metric parts. It's very easy to just look up the weight of this particular piece. Weighs 23 grams, and each of these holes is 8 millimeters apart. So it'll be very easy for us to work with these units here. So with our torque test, what we're going to want to do is take our gearbox and put on a lever arm like this, so that we can mount a weight on the end and just test and see how much this motor is actually going to be able to lift. In order to do that, you'll notice I'm gonna screw it on something like that. And you're probably thinking, hold on, now doesn't this arm itself have some mass to it that we have to take into account? Well, we can do a quick calculation on it. In this particular case, I think it's going to be fairly negligible, but why don't we do the calculation, because there's some good things that we can learn from it. And if you're looking at this, if I do mount it right here on this hole, I'm actually going to have some mass out here that is fighting the motor as it tries to lift. But I'm going to have also a tiny bit of mass over here on the other side of the center of rotation that's helping it lift. And that's one reason why, even if this is negligible, this might be a good calculation to do. Because if you do have a motor that doesn't quite have enough juice to do what you want it to do, you can add a counterweight. You can add a counterweight that might help you get where you want to be. And in order to figure out what that counterweight ought to be, you're going to be doing a torque calculation like the one we're about to do. So I'm going to draw a sketch of our beam, and I'm just going to say that I'm going to call this our center of rotation. And I'm going to draw a quick sketch of our beam, really rough sketch. And it turns out that on this side of the center of rotation, we have exactly 2.8 centimeters of length. And over here on this side, we have exactly 29.2 centimeters. And it turns out that this aluminum bar that we're going to use has a weight of about 0.72 grams per centimeter of length. So we could do a quick calculation and figure out how much mass is over here. And of course, that mass is going to act at the centroid. So that means for this, we can pretty much just call this the center. The center of this piece here is going to be half that distance, or about 1.4 centimeters from our center of rotation. And the mass that is pulling down here is 2 grams. 0.72 grams per centimeter times 2.8 centimeters gives me about 2 grams. Now likewise over here, this section is going to have its centroid approximately right here, and that is half of 29.2 centimeters, which would be 14.6 centimeters. And the amount of mass in this section is 0.72 grams per centimeter times 29.2 centimeters gives us 21 grams. Okay, so we got 21 grams at this distance, causing this to want to go in that direction. And we got 2 grams at 1.4 centimeters, causing this to want to go in that direction. Now, when we talk about torque, there's a thing called the right-hand rule. Here's how it works. If you point your thumb at you, pointing at you, then your fingers are pointing in the direction of positive torque. So this guy over here is trying to induce a positive torque on this axle, and this guy's trying to induce a negative torque. And so the difference between the two is going to be the net amount of torque. So what we're going to have is our positive torque is going to be 2 grams times 1.4 centimeters. And to get the net torque, I'm going to subtract, this is going to be a negative torque, left-hand rule, if you will, 14 point, I'll keep the grams first, 21 grams times 14.6 centimeters. And when we crank that out, we're going to get 2.8 gram centimeters minus, we get 21 times 14.6 minus 306.6 gram centimeters, for a net of 2.8 minus 306.6. So we get negative 303.8 gram centimeters. Okay, and so that means the negative means that it wants to go in this direction. That would be negative torque. That would be positive torque. Now, if we take that and we were to divide that by 1,000, then we could convert that into negative 0.3038 kilogram centimeters. And the reason I'm doing that is because then we can compare it to our motor stats for our servo motor. And our stall torque, which is the theoretical torque at which the motor can no longer lift that amount of weight at that distance. Since we're going to be testing this at 6 volts with the servo programmer, we have 21.6 kilogram centimeters at 6 volts. So that's why I converted this into kilogram centimeters. So it has this theoretical stall torque of 21.6, but that's the bare motor. And don't forget, what did we do to it? We geared it down 3 to 1. So the theoretical stall torque for our servo gearbox is 3 times 21.6, which is going to give us, what do we get there? This is going to be 64.8 kilogram centimeters. But when we add that arm on, it's going to be fighting this torque that wants to counteract that lifting. So I'm going to take 64.8 and I'm going to subtract 0.3038 kilogram centimeters. And we're going to say that leaves us with just 64.5 kilogram centimeters. So you can see, all in all, it was not a significant amount of weight, but it was a good calculation to do because there are circumstances under which it would be significant. And if you ever want to calculate an effective counterweight, that's what you would do. So let's go ahead and do a torque test and see if we can actually get 64.5 kilogram centimeters of torque out of our servo gearbox. All right, here's another quick sketch of our beam. And it turns out that I won't be adding the weight exactly at the end of the beam. It's going to be attached to the last hole in the beam, which is 4 millimeters in. So if we want to be really precise, we're going to be talking about adding a weight at 28.8 centimeters from the center of rotation. And so how much, let's call this K, for how many kilograms can we lift at that distance? Well, if our theoretical torque is 64.5 kilogram centimeters, then that should equal K, kilograms, times 28.8 centimeters. And if we divide both sides by 28.8 centimeters, 28.8 centimeters, the units, of course, will cancel, and we'll end up with how many kilograms that's going to be able to lift at that distance. 64.5 divided by 28.8, and we get 2.24 kilograms. So 2.24 kilograms is K. Now, conveniently, I think what I'm going to try to do, I have a 2-liter soda bottle, and 1 liter of water weighs exactly 1 kilogram, or I should say has exactly 1 kilogram of mass. So a 2-liter soda bottle is going to give me 2 liters of water, gives me exactly 2 kilograms. Why don't we go ahead and test this with a 2-liter bottle, and then maybe we can add a little bit of weight and see if it can actually get to this theoretical stall torque. Okay, here we go. I have got the gearbox set up, clamped to the desk. I'm going to pan down a little bit here. Hopefully you can see. I've got this synthetic cable attached to our lifting arm, and there's our 2-liter bottle down there on the floor. So let's go ahead and connect the servo programmer and see what this thing can do. Okay, here is the moment of truth. Let's go ahead and test and see if this is actually going to lift. Let's try it. It looks like it's struggling a bit when it gets to the point where it should be experiencing the maximum torque, and it's trying to actually lift the bottle off the ground. All right, let's try that again. I made a slight adjustment here. I changed I pulled this gear off and rotated it because I just wanted to make sure that we weren't up against the limit of the rotation of the servo as it is in sweep mode. So I just rotated this up a little bit to see if maybe it wasn't struggling to lift, maybe it was against running up against the limit of its rotation. So let's try this again. I would say that probably confirms it. It looks like the servo gearbox is struggling to lift 2 liters of water, which is 2 kilograms. Let's see if we can find out what its actual limit is. All right, perhaps you can see I've taken out 100 milliliters of water from the 2-liter bottle, and so theoretically this would be lifting 1.9 kilograms. Let's see what it can do. Seems to still be struggling at 1.9 kilograms. So let's try again. Okay, and let's try it again at 1.7 kilograms. Okay, so this was kind of shocking. I ended up taking it all the way down to 1.5 kilograms, and then I dumped that, and I had to get all the way back down to 1.25 kilograms. I've emptied another 250 milliliters out of this, and this seems to be the point where it can actually lift this off the ground, which is kind of shocking. It's a lot less than we had calculated. So let's go ahead and just demonstrate this. And that's the point where it can pretty much lift that bottle off the ground and hold it. So 1.25 kilograms at that distance. So let's figure out what that translates to for an actual stall torque. It's important to know that number because that's what we're going to be able to rely on when we need our robot to perform under pressure. That's what we can expect out of it. All right, so that was a little bit disappointing. We were hoping that this would be able to lift about 2.25 kilograms at that distance. And we found that our actual amount of weight or mass that we could lift was 1.25 kilograms. So let's see what that translates to for an actual torque. If we had, so our torque actual that we can rely on, that we're probably going to want to put in our chart so that we know this, is going to be 1.25 kilograms acting at a distance of 28.8 centimeters. And this is going to be we get about 36 kilogram centimeters. Okay. And then, because we're not always going to be using a 3-to-1 gearbox, we want to divide that by 3. And so T at the motor, at the output of the motor, is going to be about 12 kilogram centimeters. Let's compare that to what the manufacturer's specification was, 21.6. Pretty disappointing. We found this is actually 12. All right, we're going to have to take that into account. I'm going to try to figure out why that is, what's going on, why did that happen, and tune in to my next video when we're going to take this, and if this is what we can actually rely on, we're going to take this and we're going to look at the design of our robot and see what it means. Will we actually be able to use this 3-to-1 gearbox, or are we going to have to make modifications? Let's see what happens. Thanks for tuning in, guys. See you next time.